everybody, today we are going to start the next unit, which is over vectors. Okay, so today is just a little introduction to what a vector is and some notation of vector form. So first off, I want to point out that robots are widely used in manufacturing. One application is a robotic arm that can be used to quickly pick up and very accurately place objects. The position and motion of a robotic arm can be represented using vectors. So this is kind of the application of the real world of how vectors are used. Okay? There's a little robotic arm over there. So a vector is a mathematical quantity that has both a magnitude and a direction. Okay? So a vector has both magnitude and a direction. A vector is represented by a directed line segment. So this is a vector. A two-dimensional vector of V can be labeled as this. That's kind of vector form there. This means that this has a horizontal component A and a vertical component B. So this is the horizontal component, that's that value, and the vertical component is this B value right here. A vector is said to be in standard position when its tail is at 0. So standard position is when the tail is at 0. So like right here, the tail is the almost like the dot of your vector, and then the head is like where the arrow is. Okay, and standard position is at 0, 0 for the tail. The magnitude of a vector is the length of the directed line segment. So it's just the length. Okay. Length of the directed line segment. Okay, and this is the formula. It's the absolute value of the horizontal component plus squared plus the vertical component squared. And then you're going to take the square root of that. And it's the absolute value of it because we're dealing with distance, so you don't want it's not going to be negative because it's just a length. Okay. Magnitude disregards direction of the vector, and that kind of is said over here with the math terms. It says a vector is a mathematical quantity that's described by its own magnitude and direction. We said that. The magnitude of the vector is the length of the vector without regard to the direction. So magnitude, we kind of just need to disregard the direction there. Okay? All right. You do have to know the magnitude formula. We will not give that to you on a test or a quiz, so you do need to memorize that. All right, so let's look at some examples down here. Example A says draw each vector, vector V with a tail at 1, 2, and a head at 3, negative 2. So if we look right here, vector V has a tail at 1, 2, and a head at 3, negative 2, and then you connect from here to here because this is the tail, that's your starting, and the head is where you end. Okay? Vector U, this is in component form, negative 4, 3 is in standard position. So what that means is because we're in standard position, that goes back up here. Standard position is when the tail is 0, 0. So notice we start at 0, 0. And then the component form, remember A is the horizontal distance, so negative 4. And then B is the vertical distance, so 3. That's how you guys draw that. All right. Oh, I did forget to say the sentence right here. Equal vectors have equal magnitude and point in the same direction. I will refer back to that in a little bit, but you guys do need to know that. All right, so try these. Draw each vector on a coordinate plane. So vector V, we are at 2, negative 5 in standard position. So my tail is going to start at 0, 0. And then this is the horizontal distance, so right 2, and then I'm going to go down 5. So that would be the, oh, that was a little off. Yikes. Sorry, guys. Right there. Okay, and that's vector V. And you guys don't need to write the points, but I do want you to label the vector. Okay, you label the vector. It looks like just like the top half of the arrow. All right, and then part B says vector U with a tail at negative 4, negative 2, so negative 4, negative 2, and a head at negative 2, negative 2. So I start here and I end here. So that is vector U. Okay? And then vector t, we have a component form of 3, 3 and a tail at negative 1, 2. So this is kind of like combining two things here, so we got to be careful. First of all, we know the starting point is the tail, so I'm going to start at negative 1, 2. Component form, remember, the a and the b value represent the distance from the tail. So from the tail, I have a horizontal distance of positive 3, so I'm going to go to the right 3, 1, 2, 3. And then I have a vertical distance of 3, so positive 3, 1, 2, 3. So I would end there. And that is vector t. Okay? So that's how you draw on your vectors. Notice, so that's the coordinate point 2, 5, if you want to look at that. So the component form of a vector with the horizontal component A and vertical component B is written as this. I keep talking about that. Make sure it's in like a bracket and not in parentheses, okay? All right, next page. All right, so determine whether the vectors shown are equal. So remember we said vectors are equal if they have this have equal magnitude and point in the same direction from the first page. Vectors are also equal if they have the same component form. So there's kind of like two different ways you can look at it. So depending on what you're given, make sure you're referring to that, okay? All right, so let's see here. Determine whether the vectors shown are equal. Use in standard position, we have that drawn, and we have vector v drawn. Define the component form. We know the component form of u. To find the component form of v, you basically are just going to count the horizontal distance and the vertical distance. So the horizontal distance, you go to the left 3. So that's where that a value negative 3 comes from. And then you go down 1, 2, 3, 4, 5. Down 5. So that's where that negative 5 comes from. Okay? So these are not the same. Even though the a values are the same, the b values are not. So because the component forms are not the same, the vectors are not equal, okay? They have to be the same in order to be equal. So let's try a couple problems. It says determine whether each pair of vectors are equal and support your answers. So like I said, you guys can look at the component form or you can find the magnitude and see if the vector points in the same direction. I think component form is a little quicker, especially when you're given the picture. So I'm going to do the component form here, okay? First of all, these are all kind of pointing in the same direction, so that's kind of nice. But anyways, let's write out the component form of vector v. So I'm going to start at the tail. I go 1, 2, oh wait, these are counting by 2s. Oh, be careful. Do you guys see that? 2, 4, 6, 8, and same with the y values. All right. So from here, this is vector v, 2, 4, 6, 8. So negative 8 is moving the negative direction. And then I go 2, 4, 6, up 6, so positive 6. All right. Vector u is 2, 4, 6, 8. Oh my gosh, I'm drawing an infinity symbol. What am I doing? Forgot how to write the number 8 for a second. Sorry. All right, and then so that's there, 2, 4, 6, up 6. Okay? Or you can look at the x and y values and like subtract them from each other, kind of like they did up here. It's up to you. All right, so the component forms are the same, so yes, these are equal vectors. All right, vector u, we already know is negative 8, 6. Let's look at vector t. So let's see here. We go 2, 4, 6 in the negative direction, and we go 2, 4, 6 in the positive direction. So looking at these two component forms, these are not the same because the a values are different. So this would be no, not equal. Okay? Alrighty. What is the component form of a vector with a tail at negative 8, 6 and a head at negative 15? So we don't have a picture of this. You always could draw like a little sketch if you guys want. So negative 8, 6 would be like something like this. 12, negative 15 would be somewhere down there. So it's going to look something like that, right? If you want, though, you can also find this algebraically. So remember, A is the horizontal distance, so I'm going to look at these x values here. So I'm just going to do 12 minus -8, where I end minus where you start, all right? And the B, I'm going to do -15 minus 6. So that gives me 20 and -21. So 20, -21 would be the component form there. All right, and that should like logically make sense because the horizontal distance, if you like look at this graphically, is positive from here to here, right? And then the vertical distance is negative. Well, I have to go down, so that logically makes sense. All right, so that's how you draw those and talk about component form. All right, number 1. The hand on a robotic arm starts at 50, 120 on a coordinate grid in units of centimeters and moves to 9865. Explain why a vector would be useful to represent the change in position of the hand. Well, first of all, this robotic arm that we're talking about here, this will be brought up a lot within this unit. We're going to keep referring back to it, so kind of like picture that as we start working on it. Okay, so it says the hand on a robotic arm starts here. So that's where it starts. And it moves to that coordinate point. So this is kind of like your starting point and your finishing point. So you can think of this as your tail and this is your head. So we know 50, 120 represents the tail of the vector. And we know 9865 represents the head of the vector. Okay? A vector would be useful to represent this change in position of the hand because with vectors we can find the magnitude, and the magnitude of a vector indicates the distance. The distance between your initial and final positions. And we know the direction of the vector indicates, the direction in which the robotic arm moves. So you necessarily didn't have to write all of that, but just in general, I just want to make sure we understand. Remember, a vector is made up of like the magnitude and the direction. So we can find, or like knowing like these coordinate points of the robotic arm, we can find the magnitude and the direction, which is why we can use a vector, because we can figure out those two things. All right. Last page right here. All right, number 2, it says let V be the vector that describes the change in position of the robotic hand. What is the component form of V? What does the component form indicate in this situation? Okay, so I'm actually going to bring back this piece of paper because I need to look at the coordinate points on this one. Let's see here. So we know that the tail was 50, 120. And the head was 9865. Okay. That's what we know. Okay. So to find the component form, we're just going to do the algebra there, right? So the A value of the component form will be 98 minus 50, which is 48. And the B value of the component form will be 65 minus 120, which is negative 55. So the component form is 48 negative 55. And then it says, what does the component form indicate in this situation? Well, this means because the x value is positive, that means our robotic arm moves to the right. And because the y value is negative, that means the robotic arm moves down. So we would say, whoops, the hand move 48, are we in, what's the units? Centimeters? Centimeters to the right. And 55 centimeters down from the initial position. Whoops. There we go. Okay. Alrighty. And then what is the magnitude of V? The magnitude, remember that little formula from the very first page? You're referring back to this guy right here. Okay, so the magnitude is going to be a squared plus b squared and then the square root of that. So it's going to look like this. Magnitude of V is 48 squared plus negative 55 squared and the square root of that, and you guys can just type that into your calculator. So square root of 48 squared plus negative 55 squared, 73. And what does the magnitude indicate in this situation? Well, magnitude, remember from your notes, it's the length of the vector without in regard to the direction of the vector. So this just means that the vector moved a total of 73 centimeters, or the hand, I'm so sorry, the robotic hand moved a total of 73 centimeters. And you can say from the initial position to the final position, but just know that that's the length that it went. All right, so if you would like, I'm going to stop here. I am going to do these problems though as well. I'll just like walk through them real quick, but if you want, you can pause the video and try these, check your understandings. If you don't want to, if you want to go straight to the homework, I'm fine with that. But if you do want to try these just to see if you are on the right track before you start the homework, go ahead and pause the video and try these out and then restart the video and then listen to kind of why the answers are the answers. Okay? All right, see you guys. If you decided to do the check your understanding questions, I'm going to go over those right now. Number 3 says, if two vectors have the same tail coordinates but different head coordinates, are the vectors equal? Explain your answer. Well, in order to have equal vectors, you have to have equal magnitude and point in the same direction. So, and then also, or you could say that they have equal components. Well, we can't really find the components here. That's not going to help us. So we're looking at magnitude and the direction. So if they have the same tail but different head coordinates, those vectors are probably going to have different magnitudes. So the answer is no. The vectors are not equal because given that the same tail coordinates but different head coordinates, they either will point in different directions or have different magnitudes, right? So make sure you're looking at those magnitude and direction when you're talking about equal vectors or you're talking about the components. Number 4 says give the meaning of each statement. Okay, so this means vector S, all right, and remember this is written in component form. So the horizontal component vector of the vector S is 12, and the vertical component is -8. So that's just making sure you understand the notation of a vector. Letter B, this notation represents magnitude. So this is the magnitude of vector K, which is 27. So magnitude of vector K is 27. And then number 5, it says a student claims that vector M in component form -5, 4 and vector N 5, -4 are equal vectors. Is the student correct, and explain? The student is not correct because the vectors are not equal because their component forms are not the same. So up above, when we were looking at equal vectors, we looked more at the magnitude and the direction. But on number 5, we're actually looking at the component form because we're given that. So it's easier to just look at the component form rather than think about the magnitude and direction here. So the vectors are not equal because the component forms are not the same. Alrighty, go ahead and start your homework.